It's already doing
Yeah.
that, and so you are making sure that it is available.
Yeah, okay. Yeah, the
Right.
meeting is being recorded. Yeah. Okay.
Thank you.
Okay, Professor, you can share your screen.
Okay.
Let me first I am stopping my share. Okay.
Yeah. Thank you very much. Let me also share my screen.
One of the reasons why this is being done is I would like, as Subrato said, we are getting only a few distinguished people to this platform. The reason is that I would like everyone here to be as distinguished as you in the course of time. Thank you.
Thank you. Is my slide visible?
Yes, it is.
Yes, Prof. Clear.
Okay, now I have to take the point. Okay, thank you once again for this invitation. So let me start by giving a brief. This is not moving.
So is your slide on presentation mode or it is? Yeah.
It is in presentation mode, but somehow it's not moving. Advancing actually. Yeah, now it is. Yeah, I hope it's visible now.
But we are seeing not. Yeah. Okay.
You can see, right?
Clearly visible.
We can see, we can see.
Yeah. So let me introduce what topochemistry is. So to talk about the topochemistry, I should talk about the perception about crystals or solids in general. So this is a statement made by a Nobel laureate in chemistry a few years ago, I mean, few decades ago. The meaning of the German statement is that a crystal is a chemical symmetry. That means a dead state of matter actually for a molecule. So that means nothing can happen inside a crystal. But that perception changed when Gerard Schmidt started looking at the crystals of cinnamic acid. This kind of structure, A and B, are basically one is aromatic ring, the other one is a carboxylic acid, and also you can have styrene that will come later. So he started looking at cinnamic acid crystals, and he found that when he shined light, this did react. Those crystals did react to form this kind of cyclobutane compounds. And depending on the orientation of these A and B groups, they can have different products. And by looking at the crystal structure of the monomer, you can even predict what stereochemistry, what regiochemistry this product would have. For example, in this case, it's a different isomer than what you have here, actually. So later, this reaction was elaborated to other systems like this. This is an anthracene derivative. If an anthracene derivative is crystallized in such a way that these two anthracene rings are close proximity, less than 4.5 angstrom unit between them, they can do cycloaddition. They can undergo cycloaddition reaction when shined by light. Similarly, this kind of a triene system, this is a quinodimethyl system, which can undergo polymerization both under heat and light. And this will form a benzene ring actually, and it's a polymer actually. So there is, of course, a thermodynamic drive for this reaction to occur. That is the stability of the benzene ring. Also, one can do Diels-Alder reaction. This has been done by J. Kochi, only one or two examples. What he has done is he has taken a donor and acceptor having diene and dienophile. He crystallized and he has done Diels-Alder reaction in the crystal state. And some polymerizations also, for example, this kind of diene, diacetylenes, if you shine light, of course, this has to be proximal enough in the crystal lattice, they can undergo enine polymerization to give this kind of conjugated polymer having ene and ion, alternate ene and ion. And this is a conducting polymer, for example. And similarly, diene and also this kind of indenones can undergo this kind of polymerization reaction. Now, these are the only reactions known so far until recently, which can undergo topochemical reaction in the solid state. So some less than 10 different reactions. So we were interested in crystalline polymers because crystallinity give a lot of properties to any material, and polymer is not an exception. So we thought of making crystalline polymers using topochemistry. Essentially, idea is if you consider this red head and blue tail are complementary to each other, and if they are proximal enough in the crystal lattice, then they will undergo reaction to form a covalent bond between them. So how do we make them proximal is by using some non-covalent interaction in these monomer units, so that they will attract and they will form this kind of arrangement, and wherein you have this complementary motif at proximity in the crystal, like in here. Then it can undergo reaction in the crystal, and you can make crystalline polymers, and you can of course solve the structure of the polymer also if you're lucky. So this is the reaction we started with. This is the Huisgen reaction, wherein an azide and an alkane can undergo 1,3-dipolar cycloaddition to give this kind of triazole derivatives. Of course, if you heat these two, azide and alkane in solution, at very high temperature, you get these two products because there is no selectivity, regioselectivity, because it can undergo cycloaddition in this parallel fashion or in this anti-parallel fashion. And you get usually a mixture of 1,5 and 1,4 substituted triazole. So since it's it gives a mixture of products, it was not used actually by the synthetic chemists. But the click revolution came when these two gentlemen, Meldal and Sharpless, started looking at different catalysis. Actually, when they added copper 1 to the system, it has given only one of the products. This is the 1,4 isomer. So that is called click chemistry, a version of a catalyzed version of a Huisgen reaction. But we thought we can do Huisgen reaction in the crystal lattice if we make these azide and alkane at proximity. How do we make the proximities? By using some template here. Here I have shown some template of peptides which undergo hydrogen bonding interaction. And because of that, it forms a stack of a molecule, and the next stack is here, next stack is here, like that. And it is known in peptides that the N terminus and C terminus of adjacent stacks will be at proximity. So N and C terminus will be talking to each other in the crystal structure of small peptides. So if I make N terminus as azide and C termini as alkyne, then I can have this kind of arrangement and can do reaction along this direction to make polymers of these peptides. You can say pseudo protein actually. We started with a sugar molecule, which is this is a galactose derivative having an azide and alkane, and this is the crystal structure actually. As you can see, this is arranged in a head-to-tail fashion in this helical fashion actually. So this is a 2D picture, that's why you're not seeing the helicity actually, but it is really helically arranged. And the azide and alkane, you can see the distance between azide and alkane less than 4 angstrom, 3.2 and 3.6 between the termini. In other words, they are in a ready to react orientation in the crystal lattice. And if you keep this crystal for some time at room temperature, even at 0 degrees centigrade, it will react. You don't need to do anything. Just keep the crystal for some time and redo the crystal structure, X-ray structure. You can see all this azide and alkane vanished, and you got this triazole. So it's a single crystal to single crystal process, and this can happen at even at minus 10 degrees centigrade. So we designed several sugar-based system actually for this kind of polymerization. This is again an unprotected derivative wherein you have sugar. This is again galactose. We have got crystal to crystal, single crystal to single crystal transformation here. This is an interesting case. This is called inositol. This is similar to sugar, but it's not sugar actually. This is fully carbocycle. It's like cyclohexane derivative having OH. And this is also C6H12O6. That means it's an isomer of sugar. And you can do polymerization of such sugars. Of course, this cannot form polymerization by natural way because there is no anomeric center here actually, unlike in sugars. So we can do this reaction. And more interesting is this one wherein you have an internal alkane. Usually click chemistry requires a terminal alkane. You need a CH, acidic CH for the reaction to occur. Here, Our reaction happens because of the proximity. Just proximal placement is sufficient for us, for our system to react. So here, even internal alkyne like this can react in a single crystal fashion. This is also another one wherein we have an internal alkene. In that case, you have a methylated triazole as a product. Even more complex system like this is a this is a trahallose, actually, the disaccharide, which can be again polymerized. And this is an open chain sugar mannitol derivative having acid and alkane that can also react. That can also react to give a mixture of two products, actually. This is 1,4 substituted triazole and this is 1,5 substituted triazole. So you get a 1:1 mixture of these two products in the crystal lattice. You can say it's a blend. It's a blend of a crystal. And you can also do this reaction in peptides and also nucleic acid. This is a nucleic acid system wherein you have a cytosine derivative. And this happens in a single crystal to single crystal fashion. You can make this polymer, homocytosine polymer or a DNA. And this is with no protecting group here. Here you have an extra benzoid group. Here no benzoid group. This is also cytosine derivative. We can make this kind of DNAs. And we have several other systems yet to be published on this kind of adenine guanine systems. More work is on, our main work is on peptides, actually. So this is the start. We started with this kind of simple peptides having alanine valence system, and they react both in crystals and also in gels. They form nice gels in water and also in organic solvents. Once you remove this gel, I mean water or organic solvent, what you get is a serogel or aerogel, you can say. And when we do the powder study of this one, and this is also crystalline, very crystalline, but it's a different polymorph than the normal crystal. But from the IR data, we understood that they also have beta sheet kind of arrangement like in the crystal, but a different polymorph. And that also reacts. In this case, the reaction is along the thickness of the small fiber, what you see there. So of course, you can change the thickness of the fiber by changing the concentration of your gelator. So in other words, by changing the concentration of the gelator, I can change the degree of polymerization in this case. I have some control on the degree of polymerization. And we have seen a nice twisting all the time. Whenever we take a particular chirality, we see, for example, the normal natural amino acid, we get always right-handed helical twist for when it polymerizes. And to check the effect of molecular chirality, we have made the enantiomer of that, and we found that it goes to the other side. And it's the first example we have shown in this PNA's work that the molecular chirality has I mean, it dictates the direction of this macro molecular response. This is an interesting case wherein we have two hydrophobic amino acid. In this case, you get a nice polymer which you can use for coating, actually, to make hydrophobic surfaces. So all kinds of different kinds of surfaces we have coated this material with. For example, paper, even walls, you can coat it. Possibly we can include this in a paint, actually, to make water repellent paint, actually. So there are such possibilities. So this is a really hydrophobic material. And this is a collagen mimic wherein you have a glycine, proline glycine, which is a typical collagen sequence. We have polymerized that. And we found that this can withstand almost 1.6 million times its own weight, actually. This is a 10 milligram crystal. This is only a schematic, but actual crystal is only 10 milligram. And we have done a 3-point bending test, actually, by resting this on two pillars and by putting weight here, and 15.5 kilogram is the breaking point for that 10 milligram crystal. This is the record, actually. So I mean, this is that much strong. This is really strong because it is similar to collagen. Collagen is called biological steel. We all have a strong muscle. I mean, the muscle protein is collagen. And because of that, we could take, for example, an ant can take weight about 4,000 to 5,000 times its own weight. And that's because of the collagen in its leg, actually. So similarly, this material, this is an artificial collagen mimic, and this can withstand a lot of weight. And we are trying to look for some application with this strong material. Of course, different topology you can make. This is a cross-laminated polymer. This is a twist-stack polymer. This is a helix. This is different topologically different polymers. And this is a new reaction we have invented in our lab. We have named it as teak reaction. The previous one we have called as TAC reaction, topochemical azide alkane cycloaddition reaction. This is to rhyme with the CuAAC. CuAAC is copper catalyzed azide alkane cycloaddition reaction. That is the click chemistry. Then there is a strain promoted, SPAC actually, strain promoted azide alkane cycloaddition reaction, which was introduced by Caroline Bertozzi. So to rhyme with that, we have made it as TAC, actually the initial one, topochemical azide alkane cycloaddition reaction. Now to rhyme with this, we have made this TEAC actually, topochemical enazide cycloaddition reaction. Only difference is here we have an alkene in place of alkyne. And what you get is a triazolane instead of a triazole. And this is not aromatic, unlike in the triazole case. So that means this can release a molecule of nitrogen very easily upon shining light or even heating to give this kind of triazolane or imine, depending on the case. Now, what I'm talking about is making a triazolane containing polymer using this chemistry. Then I can change the backbone by making it to an aziridine. So I can make the triazolane into aziridine linked polymer. It's all in the backbone actually. Now, once you have aziridine is very electrophilic. You can open this three-membered ring with a nucleophile, any nuclear, for example, sugar, or if you want very hydrophobic material, you can open this with a long chain alkyl group to make very hydrophobic material, for example. So there is a lot of possibility with this kind of aziridine linked polymer. So that's the beauty of this new chemistry we have introduced. This is another example in the same series, a teak reaction, wherein you have a glycine and a phenylalanine that gives a helical polymer, which upon denitrogenation loses its helicity actually in this case. Now, coming to the main point of today's talk, topochemistry, how we can address some of the challenges in the solution state polymer synthesis, which exists in the solution state synthesis. This I have briefly talked in the introduction slide. Here we have this is of course an accidental result, not planned actually. This monomer had two molecules in the asymmetric unit. In other words, it has two different conformers in the crystal lattice. Now, this is the crystal packing. You can see this is one conformer. They are self-sorted. And the next line is the next conformer. They are also self-sorted. So you can see this is self-sorted in such a way that it can form 1,5 substitute triazole. You can see it is parallelly oriented. This is azide and alkane. And in the next line, you can see anti-parallel oriented. This will give 1,4 substitute triazole. So this alternates actually back and forth. Now, if you react this crystal, we get a mixture of 1,4 and 1,5 link triazole. These are two different polymers. You can say it's a perfect blend in the crystal actually. So that is, of course, as I said, this is not by design. This having two conformers is not by design. Of course, molecule and polymerization is by design, but not this particular blend. But anyway, that's a good result. Of course, structure dictates property. For example, only difference between graphite and diamond is their packing. Only how the carbons are packed, carbon molecules are packed. So we thought we can pack polymers in different forms. Then we are going to get different properties from the same polymer. So again, as I already mentioned, crystallizing a pre-synthesized polymer is almost impossible because, first of all, they may not be soluble to crystallize most of the polymers. Then and they won't easily crystallize. You may not have a very purely crystalline phase actually. You may have a semi-crystalline system at the maximum. So we thought our chemistry we can use, we can make monomer in the, we can make the monomer crystals and do the topochemical polymerization to get different polymers. Essentially, by making polymorphs of the monomer and doing the topochemical reaction, we can get polymorphs of the polymer. So in this case, this diphenylalanine case, we got 3 different polymorphs from a different solvent system, which I have shown here, methanol, toluene, and xylene. And of course, these are data to show that they are different polymorphs. These are powder excited data. These are cell data. Now, in the first case, this is the arrangement wherein you have a cavity, which I have marked as oval shape in oval, wherein you have 2 azide and 2 alkane. They are not in a ready to react orientation or distance. You can see the distance is 4.8 and 7.9. You don't expect a reactivity, but there is sufficient flexibility for these molecules to rotate and reach a reactive orientation. So upon heating at 60 degrees centigrade, this reacts completely along this direction, along the vertical direction. And this is the polymer structure. Now you see two dots. See, two dots are water molecules. This takes water molecules from the atmosphere during this reaction to fill the space. And that water molecules you can see easily dehydrate because these are very loosely bound to the triazolyl nitrogen, very weak hydrogen bonding. And you can get the waterless form and you can do the hydration, dehydration n number of times. You can see the temperature at which it dehydrates, which this is at room temperature to 50 degrees centigrade. If you blow dry air, it can dehydrate this particular hydrated form. And this is a TGA showing 30 cycles of dehydration, hydration. Every time it is 8.2 weight percentage of water this material takes. And this is the isotherm using dynamic vapor absorption analysis. The isotherm is also good, and it shows that it can take around at a relative humidity of 40% or so, it can take water molecules. And this is only one of the one of the polymorphs. And there are two other polymorphs, as I have already mentioned. Polymorph 2. Again, in this case, there are three molecules in the asymmetric unit for the monomer, and they react to give two different conformers in the polymer. And they are all in the same direction, actually. So you can say they are parallel. In the first case, where water absorption is there, it is anti-parallelly arranged, the polymer chains. And the third polymorph, we have only one molecule in the asymmetric unit. Again, it is it undergoes a single crystal polymerization reaction to give this kind of parallel polymer. But in this case, only one kind of conformer. Here, two kinds of conformer. Here, anti-parallel. So same molecular material, chemical structure is same polymer, but we have three different polymorphs. Packing, in other words. So we have done with other system. This is again a peptide system having alanine and valine. This is a DL peptide. One is D amino acid, the other one is an L amino acid. We got two different polymorphs. These are again cell data. Here you can see these are parallelly arranged. All the heads are in the same direction. And the next polymorph, they are anti-parallel. You can see adjacent molecules are in opposite direction, the C and N terminus. I have shown with the background arrow mark. So they are going back and forth. So this is anti-parallel beta sheet. This is parallel beta sheet. So upon reaction, they undergo complete polymerization to give this parallel polymer and anti-parallel polymer. Again, molecularly they are same material, but we have two different structures. Even sugars, we can do this kind of polymorph, topochemical polymerization of polymorphs. This particular one, this is inositol, as I have already mentioned. We got three different crystal structure, and these are data TGA. Sorry, these are powder XRD. This is a DSC showing different melting points, and these are cell data. These are also to show that they are different, really different materials, different crystal structure. And this is polymorph 1, wherein we have two different conformers, conformer A and B. And you don't expect any reactivity. As you can see, the distance between them is about 6.8 in one case, and in the other conformer it is 7.0. So you don't expect any reactivity here. In the polymorph 2, there are 2.5 molecules in the symmetric unit, and of which only one of the conformer is self-sorted in a reactive distance, which is 3.8 angstrom unit. And this is too far, actually 8.2. In this case, it is 8.8. So you expect about 40% reactivity here at a maximum. And here again, you have two different conformers A and B, of which one is self-sorted in a good distance, reactive distance of less than 4 angstrom unit. The other one is quite far, it's 7.7. So you expect 50% reactivity. But actually, all of them reacted to 100%. These are why? Because these are thermal reaction. We need to heat these crystals, and the distance what we are seeing is in the static state when the crystal structure was taken either at -100 Kelvin or even at room temperature. But those are static picture of a dynamic system. Actually, when we heat, these molecules can rotate, can move, and reach a orientation for reaction. And that's what is happening. All of them reacts to 100%. These are the data showing, these are NMR data. This is powder XRD data, actually, sorry. Powder XRD data showing full polymerization this takes different times. Actually, this was 35 hours, this is 48 hours, this is 32 hours. All of them reacts to 100% actually. Now we have also done another system which is a square amide, which is known to be a highly hydrogen bonded system, and it can form either parallel or anti-parallel stacks like this, which is known in the literature if you have square amides with having two alkyl groups. So we thought of introducing our azide and alkyne. Of course, we also need a chiral motif, which is an amino acid serine. For inducing chirality, we are interested in polymers which are chiral polymers for separation as a stationary phase for enantiomeric separation. So that was the initial idea, to make this kind of a very highly hydrogen bonded system, which should be insoluble in any material, any solvents. So we made this material, exactly this material, monomer M. We got two different polymorphs, polymorph M1 and M2. Again, different data, melting point and DSC showing they are different. And here it is here is the packing actually for the first case, polymorph 1. You can see these are one stack of monomer, next stack of monomer, and they are arranged in a beta sheet kind of arrangement, an extended kind of arrangement. There is no twist here actually. In the other polymorph, this is already half helical. The molecule is half helical because of the serine unit here, and it forms a supramolecular helix along this direction. And there is another difference. Here, all the stacks are on the same direction, parallel. And in this case, they are anti-parallel. One stack is along this direction, the other one is in the opposite direction, and this repeats like this. So if you look at along this direction, it is forming a supramolecular helix, and this is still monomer. Now, if you heat this reaction and heat this crystals, both react. These are powder XRD data till end of the reaction. Both of them reacts completely. And you can also solve the final crystal structure by single crystal X-ray diffraction. This is the first case. You can see this is polymerizing along this direction to give this kind of connecting between the adjacent stacks, forming beta sheet kind of arrangement. In the other case, it is forming helical, fully helical polymer, or it's not really alpha helical, it's a helical polymer. So all these are single crystal to single crystal transformation, because of which we can solve the structure of the final polymer. So this is again the crystal structure, showing the left side is the one which is beta sheet kind of arrangement. There is no helical twist. In the other case, you can see there is a helical twist in the right side. And also this crystal break and expand during this reaction. Now the question is, can we make structurally different polymers? Structurally in the sense the chemical structure. Nature does this a lot. For example, glucose. Nature used glucose to make cellulose and starch. They differ only in the anomeric stereochemistry. One is beta, the other one is alpha. And also 1,3-beta glucan. Here, nature plays with the regiochemistry. Here, this is linked by 1,3 position, and cellulose it is 1,3. Both are beta, but the regiochemistry is being exploited to make different polymers by nature. Another example is isoprene. Isoprene, natural rubber gives a cis polyisoprene upon polymerization. Same isoprene upon polymerization gives, with another enzyme, it gives a gutta-percha. This is another plant. This gives a trans polyisoprene. So can chemists make this kind of different polymers from the same monomer? That was the question. Answer is yes. We made this particular material to make nylon mimics. Actually, the nylon 3M nylons actually. These are having carboxylic acid having 3 units, that is malonic acid, and an amine. So such nylons are very difficult to synthesize by normal nylon synthesis, because this dicarboxylic acid decarboxylate at high temperature of nylon synthesis. So you cannot make easily nylon 3 and N is series number actually for the diamine part. So we thought using our chemistry. So how we plan to use is make a malonic acid derivative having azide and alkane. So in other words, we are splitting the amine as two parts and connecting at the end, and later we are connecting these two amines as the polymer grows. So we got two different polymorphs in this case, polymorph 1 and polymorph 2. These are again data. One is anti-parallel, as you can see, the other one is parallel. And the distance is again so good for the reaction less than 4 angstrom unit in both the cases. And yeah, in first case, it reacts connecting the adjacent stacks. These are anti-parallel stacks, as I have mentioned. This is connecting adjacent stacks, the polymerization along this direction, the horizontal direction. And to form this kind of polymer having 1,4 linkage. This triazole is having 1,4 linkage substitution. Or in other words, this reaction, this polymerization reaction is connecting the stacks along the horizontal direction. In the other case, the polymerization along the vertical axis, along the same vertical axis and forming these kind of linkages, which is 1,5 linkage. They are adjacent actually, these linkages. So this is a different polymer. And of course, this is parallel as I already mentioned. So here is the brief of that. We can synthesize this particular monomer and crystallize to get 2 different crystals, polymorphs. And one can give this kind of extended 1,4 link polymer, 1,4 triazole link polymer. And the other one can give 1,5 triazole link polymer. These are really different polymorphs. Sorry, different structures, polymers. Another interesting feature is, interesting area is helical polymers. People are interested in helical polymers for different applications. So again, as I mentioned, we started with this proline containing polymers. Proline gives a twist actually for the peptides. So glycine, proline, glycine. This is a sequence for collagen. So we have used this kind of monomers, having this monomer having azide and alkene. Then this is the structure wherein this is arranged in a helical fashion in the monomer. And it's a good distance here, 3.5 and 3.5 angstrom unit between the unit. And that reacts and you get a helical polymer along this direction. Of course, in this case, it is triazole. It's not triazole. You can remove a molecule of nitrogen and you can change its helicity also. So there is, and also we can substitute other nucleophile with the triazole, which we have not done for this case actually, but there is a possibility. Of course, depolymerizable polymers is very important. Usually, triazoles are rock stable material, so you cannot do retro click reaction or retro azide alkene cyclohexane reaction. But of course, you know that diel salt reaction can undergo retro diel salt reaction, or you can go back to monomer. But no one has tried ever for synthesizing a polymer using diel salt system in topochemical fashion. So we thought we can take such a simple monomer having this kind of furan derivative, feroic acid as the diene, and this has a dienophile, Millikan head as dienophile, and we can make such a simple system. And this is the monomer structure. Crystal structure, you can see diene and dienophile are in the ready to react distance 3.9 and 3.6 between their termini, and they react. They react in a single crystal to single crystal fashion. This reacts at room temperature also, but it takes 1 year for the reaction. But if you want quick reaction, you can heat it in 12 hours, it's completely react. So there is a possibility of, if you want to solve the crystal structure, we have done very slow reaction so that we don't disturb the crystal much. So that's how we got CSE crystal structure later. But we can fasten the reaction by heating it up. We can do the reaction in 12 hours. Yeah, this is the polymer structure. This is giving an XO product because this arrangement is in an XO fashion. So the selectivity is due to that arrangement. Usually diel salt reaction favors endo product, but here what matters is not what matters is the arrangement of molecules. So this was arranged in the crystal for XO kind of arrangement reaction. So this gives XO selective product. And that undergoes reaction, retro diel salt reaction at high temperature. You can see this is TG, you can see that. This is another system wherein we have again azide and alkene. As I mentioned, it gives a triazole, and once it removes a molecule of nitrogen, it can either form azarine or imine. They are isomers. In some cases, we get imine, some cases we get azarine. We are currently looking at what decides which is the product for azarine or imine. We have some early clues, but we are not confident enough to say anything what gives what for this kind of system. Nevertheless, there are some system we can give this kind of imine. So once you have imine, it's very easy. That means imine can be easily hydrolyzed to amine and aldehyde by putting a little bit of acid. So in this particular case, having this valine and phenylalanine system, we got this denitrogenation. You can see the bubbles of nitrogen escaping this when you do this crystal heating in oil or any solvent where it doesn't dissolve. If you heat or shine light, you can see the bubbles of nitrogen coming out. This is in oil, I believe. And yeah, of course, you can see the denitrogenation by TGA also. And what you get it here is an imine. Actually, this is again single crystal. Despite having this kind of loss of gas molecules, we thought it will be really porous and it will disturb the crystal. It did not. We could solve the crystal structure even after the imine stage. Now, if we want the monomer, not really the monomer equivalent. We started with an azide and alkene, but once you put acid, you get an amine and aldehyde. Of course, this can be polymerized further, right? Amine and aldehyde, you can do the condensation polymerization to make this imine again. So we have a formal depolymerizable polymer. This is not really monomer, but monomer equivalent, which can be polymerized. 2D polymers are a very interesting system. No, this is not possible in solution phase polymerization. If you have a monomer having two ends of two reacting ends, two reacting chains on both sides, then it will give a very, very complex networked entangled polymer. You will never get a 2D polymer like this in a sheet, because the molecules are free to move in solution. So, but in topochemical fashion, we can synthesize this kind of 2D polymers. We started with this kind of diazide and dialkane containing benzene ring. I mean, this is a very simple system. And here is the packing. Again, there are two molecules in the asymmetric unit. They are packed one after the other. This is the one conformer, next conformer, then again the first one, like that. So they are stacked one after the other like this. And with a distance, good distance for the reaction between azide and alkane, 3.4 and 3.3 angstrom unit between them. Now, in this fashion, they can react. Now, we have two more reacting units, right? The one azide and one alkane is still remaining for each monomer. So this is one stack. This is next stack. You are seeing stack through the stack direction. So that means stack is going behind the screen. So between the stacks, again, they are at proximity. They can react like this one. So that means it can react behind the screen and also along this direction. So you are going to get a 2D polymer if that reacts. Yeah, this reacts in a very sequential fashion. If you do the DSC of this monomer crystal, you can see two exothermic peak. These reactions, of course, exothermic, azide alkane cycloaddition reaction is exothermic. You can see one hump here, the first reaction. This is the second reaction. This is final decomposition. So if you heat until 160 degrees centigrade and do the DSC again, you will see that this is vanished. That means this reaction is completely over when you heat till 160 degrees centigrade. Then we have only one exothermic peak for the next reaction and decomposition. Now again, if you heat till 200 degrees centigrade, 210 degrees centigrade, both vanish. So it suggests that this experiment suggests that these reactions are sequentially happening. So yes, we have done this reaction in the crystal phase also. We have heated till 160 degrees centigrade at 2 degrees centigrade per minute. And we have solved the structure. As you can see, it's reacted along the stack, forming one phi linkage. So this is one polymer. You are seeing the polymer through its axis. So now if you heat this again further till 200 or so, you can see this is again a ready to react distance. This reacts to form this kind of 2D polymers. Now you can peel off each of these layers or few layers by soaking in some solvent and putting a little bit of acid. When you put acid, this triazole nitrogen get protonated, and because of the proton-proton, I mean positive repulsion, this get exfoliated, and you can get layers of this 2D polymer. So this is really hierarchical. So monomer, 1D polymer, 2D polymer, then sheets. Of course, in the second polymerization, you can see this kind of bending. What happens is all the crystal bends to form a crescent kind of shape and then go back to the original shape when it is fully polymerized. So this is due to the strain which is developed in the crystal lattice because we have both 1D polymer and 2D polymer halfway through. So that's a strain. This is a bimorphic state. When it is in the bimorphic state, it bends to release the strain. When it is fully reacted, it goes back to the original, normal structure. Yeah, this is same. Also, we have seen this 2D polymer. Once you completely polymerize, you get a straight crystal after the bending. Now, if you apply force, a 3-point force again, to 001 phase, it gives an elastic bending. I think I have a video. I don't know whether I can show this. Anyway, I think I have to come out. So this bends and it reaches back to the original position if you put pressure here. But if you, on the other side, this is another phase. If you put in this phase, 010 phase, it undergoes a plastic bending. You can arrest at this. I mean, you can stop at the stage and it still preserve that kind of arrangement. So depending on the phase. Okay, I can see. See, this is the first one is an elastic bending. The other one is a plastic bending, depending on the phase, which phase you are giving the pressure. And interestingly, this shows an optical waveguide property. So this is done in collaboration with one of my colleagues in physics department. So he has shined laser light for 20 nanometer, and he has collected the emission from the other end of the crystal. And by changing the position of a radiation, you can collect always at this position. And he has seen that there is a new peak which is coming, and initially there is only blue emission, and then towards then there is a green emission. And when the light travels through the crystal for a longer time, the second light is increasing. We don't know actually what is happening. We are now currently talking to some photochemists and photophysicists what is happening here. So something is happening, and the green emission is increasing actually when we change the distance. When the light travels through the distance, some of the absorption is happening and giving a lower energy spectrum. This is the same thing. Stereo complex, I think I will finish in 1 or 2 minutes. So this is a stereo complex. Stereo complex means usually polymer chemists are interested in stereo complex. This is like racemic mixture for simple chemist. So if you have a polymer having enantiomer pure polymer, and if you have the opposite chirality, if you mix them together, that is called stereo complex. It is never called as a racemic mixture because polymers having all kinds of sizes, right? So it may not be 1:1 match actually. So it's never called as a racemic mixture. It's called stereo complex, but essentially the idea is same. So you have both in equal amount by weight. What is expected is this one, a perfect blend of one chirality and other chirality. But what you get is a mixture of all kinds of things. You have coiling, you have this kind of looping and self-aggregation, etc. So we thought we can use crystal chemistry to make this kind of perfect blend, perfect stereo complex. So we started with this kind of azide and alkane containing inositol derivative, but this is a meso derivative. And of course, in the crystal, they form this kind of enantiomer, conformational enantiomers. They are not really enantiomers, but conformationally enantiomers. These are called conformational enantiomers. They are self-sorted, and they react in a crystal to crystal fashion, giving perfect stereo complex. This is a polymer having only one chirality, R chirality, and next one is S chirality, and back and forth you can get this kind of perfect stereocomplex because of the crystal arrangement. And yeah, this is ladder polymer. The last one is a ladder polymer, where we have this kind of, again, this kind of system having 2 acid and 2 alkane, and this is arranged like a ladder actually, and they undergo reaction to give this kind of, this is all a single crystal reaction. So now we have large cavities between these styles, right, ladder. So we can encapsulate best, and this kind of ladder polymer, of course, you cannot make in solution, and 2D polymers you cannot make in solution, because it can react randomly and can give a very complex 3D network. Of course, this is again, we started making this kind of donor acceptor co-crystals to see their electronic or electrical properties. We just made these 2 monomers co-crystal, and we have reacted and made polymer, but we are yet to study the properties. This is currently going. So this you can see the Axiplex absorption, monomer and donor acceptor, and when you have donor acceptor co-crystal, you have a change in absorbance in both the cases. We also do gels for different applications. So this is one application. I thought I did not have this slide, but briefly I'll discuss. So this kind of gelators we made to make gels of oils and hydrophobic solvents to give this kind of optical soft optics actually. These are oil gels. Oil has a refractive index of glass, 1.5. So we can make glasses, soft glasses out of this, basically gel, to make prisms and lenses actually, which are working prisms, which are working lenses. And this is also self-healing. Usually this kind of gels are self-healing. So this is a scratch-free optics, you can say. And we also made this kind of conducting polymers using gels. So it's the same topochemistry using gels actually. Briefly, I mentioned about diene chemistry. We can make diene gelator and do the polymerization in the gel and make really conducting clothes. Actually, we have made conducting clothes. And also several other applications we have shown using gels. I think I have overshot with time. I'm sorry for that, but to conclude, yes, I have put a K here. Those of you understand German, this means that a crystal is not a chemical cemetery. This was a wrong perception people had. The crystal is a chemical cemetery. That's not. It can do a lot of things, and it can do. I have shown you that we can make crystalline polymers, 2 different polymers in a single crystal, then different polymorphs of polymer, helical polymers, etc. And with that, I should conclude by thanking my students and finally you all for listening to me. I'll be happy to take questions.
Very nice, very nice. A fabulous tour through this graveyard of materials and making them alive. So that's great. One thing that for all of you to know is that Professor Sureshan is probably the most productive person who publishes only in these frontier journals. And maybe he has the maximum number of Angavante papers in the shortest possible time that if you look at in our history here. So this will all be enthusing people here. But then let me ask a few questions just to get it going. We should have had more time actually, but unfortunately that is not there. The moment you say crystal is reacting through reaction, of course, goes through transition states, mechanisms, whatever. So obviously there is space required, and people must have asked you these questions before. So space would mean that deformations, and you showed deformations in some cases. That would mean that at one point where deformation is impossible, the reaction should stop.
Yes.
So I wonder whether you explore this, a critical state at which reactions stop.
Okay.
And is that something to do with the Young's modulus, something to do with the elasticity? What is it to do with? Is there a correlation? So that is one question that I wanted to ask.
Okay. Shall I answer that now?
Yeah. Go ahead. I mean, I have a few questions. Yeah.
So in this case, yes, you're right. If the system is really hydrogen bonded, for example, when we have a system which are sugar derivatives without any protecting groups, they are reluctant to move. These acid and alkane are reluctant to move because there is strong hydrogen bonding interaction for the rest of the molecules, and they don't want to move from that position. So even if we heat, they don't want to react, even though the distance is good, almost good to react, but doesn't react. But when we have system where the molecules are weakly bound, for example, fully protected sugar, we have examples which I have not shown for today. The molecules rotates 180 degree, the whole molecule, which is also unheard of actually. The whole molecule rotates in a single crystal to single crystal fashion and forming a new polymer, and from there it's reacting. So it all, I think, depends on the interaction energy between the molecules, whether they want to move from the position. If it is really strong, they don't want to move. So in our case, later we realized this one and we started putting a CH2 before N3 or alkane actually. So that gives a lot of flexibility, having an sp3 center, and that can still move or at least rotate around that single bond and reach a position. When we don't have that, it is really sometimes reluctant to react. But
Good. So let me, I mean, for want of time, let me quickly go into a few other things. You talked about collagen and the strength, enormous strength. You know, this interest in materials and applications and all that. So collagen is great, but it is cruel. Collagen is cruel. You have something, there is no cruelty. So I'm just wondering if we can make this in scale. You are having leather without cruelty, right? So I would say it is now, I would say leather with love, right?
yes.
So I'm wondering whether it is possible. And if that is possible, of course, you can, that's a business that is there. So of course, there are associated questions as to what it costs and things like that. So scalability and all that. So can you answer this?
Yes. So we thought about this. We had 2-3 collagen mimics. One of them is fortunately soluble in water to some extent, the polymer. And we were planning to make bond substitute. Yeah, our bond is nothing but collagen mesh and calcium phosphate, hydroxyapatite. So we of course, we don't know this biological, I mean, we can't do the biological studies here. So we collaborated with some people in Sri Chitra. And the problem is they are immovable people actually. They are very slow. But at least they have done some test to show that these materials are safe. So that much study they have done. And the growing the hydroxyapatite and the making the mesh and making the bond material, we have not done. They said they are interested, but really it has not started. But it is in our agenda to make this kind of bond replacement material using this kind of material. Leather, we did not think of. I think leather is more complex than collagen. I really don't know the structure of leather. Maybe it has other proteins also.
But yeah. So point is, it is strong.
Yeah.
And it can be made at scale.
Yes.
The fundamental building block, if that is possible, then you have leather with love.
Yes, maybe a blend with some other polymer, it should be possible. This which I have not thought about actually. It's a good
So
choice.
what is the cost of it?
Cost is much cheaper than collagen itself. Collagen is quite expensive, though it is naturally available. The process is very tedious to extract.
So
collagen.
please think about it. If you think it is interesting, we can look at that. My last question is that you talked about 2D thing. It's great. You are getting a graphene or molecular equivalent of something. There is a lot of possibility with conductivity, what have you. all those possibilities. And if with all the strength and all that you talked about, then this is going to be a material which is what everyone would like to have on their clothing, skin, bulletproof, whatever.
Yes.
So I'm just looking at this material. Is it possible truly? And I don't know if you put it on a glass, the glass is non-scratchable or whatever, unbreakable. So there's a whole lot of possibilities in 2D polymers. I'm wondering whether this has been looked at.
No, we did not look at it. Only issue is that we have to put this in the whatever surface we want to make this. We have to put this monomer at the monomer stage and then polymerize there itself. Because once we polymerize, it's insoluble. It's not solution processable. To coat a surface is very difficult. But it's possible to synthesize there itself. I mean, in situ on a surface. That we have to crystallize a thin layer of material and crystallize, but I have not looked at it actually, that possibility of making scratch-free glasses or things now.
So any form of mechanical transformation requires energy. And that energy, you can, of course, when you transform something, you also have a delta H. And you are going downhill, and so you're releasing something. I'm just wondering whether any of these possibilities, whatever that is happening, has it been used to harvest energy or convert energy, create energy? So you have a molecule which makes a new bond, of course, delta H is released.
Yes. So, that's why we see most of the time this crystal bends, and sometimes they break, sometimes they pop actually. So in one case, we have stored this energy. Again, I have not shown, that's not a polymerization, that was just a dimerization. In that case, if it is reacted slowly, the molecule is intact. I mean, the crystal dimer is intact. If you quickly increase the temperature or quickly heat it, it explodes, pops actually. Reaction happens completely, but it pops. And when it happens slowly, what is happening is it is sucking water from atmosphere, again, like in the previous case. And that water is stabilizing the crystal, and that energy is not, I mean, it's not getting popped. But if you are suddenly heating, it is popping. So now we have stored in water. I mean, slowly heating, that we have energy stored in the form of water. Now, if you suddenly heat that, we can make that explosion happening. So we have made this as in the lab scale, we have made a switch out of that. If there is a sudden rise of temperature in any circuit, for example, an unmanned vehicle, space vehicle, if there is a sudden rise of temperature, this will immediately pop up and it will break the circuit or start the new circuit, a recovery circuit. All those things are possible. We have shown a switch actually using this. It happens only when that sudden rise of temperature is there. So it's a kind of storage of energy which can be released at high temperature.
Subrata, you take it forward.
Yeah. So any other questions, or shall I go ahead? Anyone have any questions?
Yeah, I have.
Oh, yeah. Okay.
Thank you so much, Professor, for the very interesting talk. I have what are the monomer you are selecting? You are designing, or you are looking for some CCD from some database? The monomer which you are selecting, on what basis?
Yeah, so this not CDC anymore. Previously, we used to do that, the kind of peptides. The skeleton, of course, we know peptides have either beta sheet or some helical conformation. If it is smaller peptides, usually beta sheet kind of arrangement. So now we don't look at CCDC for making what sequence we want to make. Sequence we choose by property. For example, collagen sequence we have taken for a property. And also the diphenylalanine, which is also taken for a property, because that is not to form aggregates, especially A beta peptides, for example, that has this diphenylalanine, which is the nucleating center for the aggregation. So and also the hydrophobic material we have seen, the coatings which can be used to coat the surface. Again, where we have used two isoleucine and leucine, these are hydrophobic amino acid. So essentially, by looking at the property, we are choosing the peptides. Now we are trying to do the tyrosine and hydroxylated tyrosine to make a sticky material. For example, the mollusk and some aquatic organism have very sticky ability to attached to surfaces in water, actually, using this protein having a lot of tyrosines. So we are trying to do such kind of function based.
Okay. In one case, you mentioned about the molecules rotate for the this polymerization. So during the rotation, is it forming the new phase, like a different kind of polymorphs?
Yeah, in some cases, we could observe a new polymorph and we can even solve the structure. The one which I have talked about, which is rotating 180 degrees, there is a clearly isolable polymorph. But in most of the time, it's a transient state. It reaches a transient state and reacts. It's not a really stable polymorph which you can characterize most of the time. It's
Okay,
only
thank,
vibration. We can say it's a vibration and reaching a reactive distance.
okay, thank you. I have another question related to your bending crystal. So during the bending of the elastic and non plastic, do you expect some chemical environment change? And if it is so, how you can detect them and characterize the chemical environment around the bonds if it is bending?
No, this I did not think about any chemical. There is no chemical reaction. There is no chemical change. But of course, environment changes, right? There is a strain actually at the bend position. There will be strain. I don't know how to
Characterize them? Like
maybe ramen or something, the bond energy or something. I did not think about, but that's possible, I think.
and another case where you mentioned about the optical waveguide, you said like the more the distance is traveling is converting from blue to the green one.
Yeah, yeah.
So why it is so? Because the energy
Oh,
loss
that's
and
I already answered. I don't know the answer. I am talking to some
uh,
physicist and a photochemist.
uh, was your system was luminescent before the
Yes, yes. Even monomer said it is luminescent because this is a kind of push-pull system, right? You have NH2 and COH, two NH2 and two COH in the benzene ring. So
oh,
that is luminescent.
oh, thank you so much for your
Thank you.
Okay, so let me finish two questions quickly. Okay, first about designing of your monomer. So in most of the cases, you have taken azide N3, yes, covalent azide with sp3 bond, sp3 carbon, right? Now there is possibility to make that sp3 carbon like one hydrogen, like replaced with any other group. And another possibility is that you are taking alkyne or alkene as a terminal. Now, if you consider alene, double bond, C
Understood.
double bond. Yes. So that kind of any system, did you try for it? Alene system, I am basically interested for alene.
No, we did not look at it. Aline
Okay.
should work. Aline should work. I don't think that. I mean, Aline should be more reactive. In fact,
Yes, that's right. Yeah.
expected. I did not look at it now. So
And
now we are doing some other system like nitrons and
sulfone. Oh,
and also nitrile oxide. Mainly we are doing cycloaddition reaction. Of course, this also cycloaddition it can happen. We did not try it with Aline.
and this any kinetic study is there? Like this is happening as the same 2+2 or 3+2 same way. I am talking about the mechanism in the crystalline phase. Is it the same as we used to do, or like as we used to do in gaseous phase, like two molecule reacts or
Yeah, okay. Kinetics.
kinetic? Yeah.
We do kinetics. Always we get a sigmoidal curve. Of
Yeah.
course, that is expected for a topochemical reaction because of the cooperativity. We don't study much of kinetics actually, other than this. Just time versus percentage. We do that, but not mechanism. Mechanism is clear actually. It's a proximity-driven reaction.
And how is the changes in the powder Excel? Let's say we have this crystal A. Now that crystal inside crystals like molecules are reacting, right? So for that, how is the changes in the powder exerting? Like is the powder exerting of your product, polymer product, obviously will be different compared to monomer.
Yes,
So reflecting in the powder exerting.
yes. Clearly, there is a shift. Usually, some major peaks are shifted, some peaks vanishes. Of course, you cannot say which one, right? So there is
Yeah.
a clear shift.
Okay. Yeah. Okay, I am done. Anyone else? Anything? So we are actually crossing the time 3 minutes. We started around 7:15. Okay. So
Maybe I have taken more time. I'm sorry for that.
no, okay. I thought. Yeah.
please see whether there are other questions, and otherwise we can close it. But then it was a phenomenal thing. It opens up a whole lot of possibilities. I wonder whether you can do something in droplets. These flows can be pressurized in droplets to do something more.
Okay.
That's a thought that is coming to me. Of course, from among the things that I asked, I was particularly excited about the love. I was particularly interested in that. Cruelty is a serious problem. Yeah. So if you can build that into some tech, it may be very much useful.
Think about it. Yes. Thanks.
Okay. Subrata, can you conclude then?
Yeah, so thank you, Professor, for this wonderful lecture. By the way, we are meeting again on April, so one mail will be intimated to you, so by another professors in the April, okay? So I'll convey the date, exact time and everything. Okay, thank you. Shall we conclude or you are going to say anything?
Nothing. You are concluding. Yes,
Oh,
you are
thank
supposed to be concluding this.
Okay, thank you.
Thank you. Thank you, everyone. And let us enjoy wonderful science. Yeah, thank you.
Yeah.